Mendelism Part 3. So Mendel's principles can be used to predict the outcomes of crosses between different strains of organisms. There are three methods: Punnett square, fault line, and probability. So we have learned the Punnett and fault line. So we use the solve probability to help explain genetic events. So genetic ratio like 3 to 3 out of 4 tall, 1 out of 4 dwarf, they are thought as probabilities. So we can predict the outcome of each fertilization event. Probability of zygote becoming tall is 30 to 4, dwarf is 1 out of 4. Probabilities range from 0, meaning that it doesn't occur, to 1, which is event is certain to occur. So the product law, we have learned this before, it is 2 or more events with no probabilities occur independently but at the same time. So you have probability of 2 or more events occurring simultaneously, it is the product of the individual probabilities. 2 or more events are independent of one another if the outcome of each one does not affect the outcome of any of the others. Okay, so now again, the example of 2 coins. So coin toss 1 does not affect coin toss 2. Okay, mean that there is no rule in that you cannot toss the second coin after the first coin. So you have coin 1 and 2, you have head and tail. So you might have the head tail, tail tail, or tail head. All of these would have 1 out of 4 outcomes. The probability of obtaining a head or tail is either 1 or 2. Outcome of one coin is unrelated to the outcome of the other coin, and all possible combinations are predicted to occur with equal probability. So sum law happens when you have outcome of 2 events are dependent by one another, but one can be accomplished in more than one way. Mean that to actually get to A, you can either do X only, maybe X and Y, maybe Y only. Mean that you have more than one way to get to the thing, to achieve the thing. What is the probability of tossing a penny and nickel, obtaining 1 head and 1 tail? So in this case, you don't actually care about the order. You can have tail first, or maybe you can have head first. Okay? So head, a penny and nickel, or nickel and penny, both are counted. So there are 2 ways in which the desired outcome can be accomplished, each probability of 1 out of 4. The sum law, you have the probability of obtaining any single outcome. That outcome can be achieved with 2 or more events. It is equal to the sum of the individual probabilities of all such events. As according to sum law, overall probability in our example is equal to 1 over 4 plus 1 over 2 to get 1 over 2. So meaning that to actually get 1 head and 1 tail, okay, you toss a 10 cent and 20 cent, right? Toss the 10 cent, you get head. Toss the 20 cent, you get a tail. But what if you also count the one which is 10 cent, you get tail, and then you toss the 20 cent, you get head. As long as you get 1 head, 1 tail, they are counted. So we count them both together, you get 1 over 2. So in this activity, we learn about sum law. First question is, a single 6-sided die is rolled. What is the probability of rolling a 2 or a 5? And in a group of 101 students, you have 40 juniors, 50 female, and 22 are female juniors. The probability of a student picked from this group at random is either a junior or a female. Right? This is the answer. A single 6-sided die is rolled. To get 2 or 5, you roll and roll and roll. What is the probability to get 2? 1 out of 6. What is the probability of getting a 5? 1 out of 6. So we have 2 of these events, both are counted. So plus 1 and 1 together. So it is 2 out of 6. Okay. You roll and then you get 2. That counts. You roll and then you get 5. That also counts. So it is 2 over 6 or 1 over 3. Okay, what about number 2? Junior is 40 out of 101. Female is 50 out of 101. So since it is all, means one or the other, not both. So we must subtract the ones who are both. Okay, so 40 out of 101 plus 50 out of 101 minus 22 out of 101, you get 68. To know the result of a cross, calculate the probability of each possible outcome. The result will allow us to predict the proportion of offspring expressing each phenotype or each genotype. What's important? Prediction of possible outcomes are based on large sample sizes. Biases actually do happen. In prediction, you might think that if you have 9 out of 16 would be having both dominant. In reality, it is unlikely because there might be a deviation in smaller sample size attributed to chance. But the bigger sample size, the smaller the error. So we have Binomial Theorem. So Binomial Theorem, bi means two, nomial means name, meaning that you can either have event A or B. So in Binomial Theorem, we can use it to analyze cases with alternative ways to achieve a combination of events. So just like the tossing of two coins, you can have two heads, right? You can have both of the first coin you have head, maybe the second coin having head. Okay. So for families of any size, we can calculate the probability of any combination of male and female children. So for example, what is the probability that a family of 4 children, 2 will be male, 2 will be female? So this question does not specify the order, right? So you can have either male, female, female, male, or maybe male, male, female, female, maybe female, female, male, male, or maybe female, male, female, male. Means that you don't actually care about the order as long as it happens. Okay, so this is the expression of the binomial theorem. A plus b to the power n equals 1. A and b are the probabilities of each event or each result, and n is the number of trials, how many times you try. Let's say you want to have how many children? Maybe 7, so n is 7. So here is the Pascal Triangle. As the value of n increases and the expanded binomial becomes more complex, the Pascal Triangle is a useful way to determine the numerical coefficient in each term of the expanded equation. Starting from the third line from the top of the triangle, each number is the sum of the two numbers immediately above it. So let's look at the demo of the Pascal Triangle.
Okay, so this is how we do a Pascal Triangle. First of all, you draw a 1, 1, and then 1 plus 1, what do you get? 2. 1 plus 0, you get 1. So next example, 1, 2, 1. So 1 plus 2 is what? 3. 3. 1 plus 0 is still 1. Next level, 1 plus 3, 4. 3 plus 3, 6. 1 plus 3, 4, 1, 1. Next, 4 plus 6 is what? 11. No, sorry. It's actually 10. 10, 5, 5, 1. Okay, and then what's this? 6, 15, 20, 15, 6, 1, and so on. So this is your Pascal triangle. Okay, so this right here is a level 0, 1, 2, 3, 4, 5. Sorry, actually it should be maybe like this. Level 0 should be the top where it's just 1, right? So now you get it. 2, 3, 4, 5, 6. So this number all correspond to n. N is what? These right here are all the coefficients. This is what you get. Pascal Triangle.
To expand any binomial, the value exponents of a and b, like a1, b2, a3, b2, are determined using the pattern. Let's say you have a plus b to the power of n, and then you would start with an minus 1b, an minus 2, b2, an minus 3, b3, meaning that the power of A is getting lower and lower and lower until it is A to the power 0, meaning that A to the power 0 is what? 1. And then B, from having B to the power 0, it starts to have more power. If you can see, B and then B2 and then B3. Okay, let's say the number of n is 7, right? So A plus B to the power of 7. So we start with what? What is n? 7. So we start with A7. Then next, A n minus 1. What is it? 7 minus 1 is what? 7 minus 1 is 6. So A6B. And then what's next? A n minus 2 B2. So we have A. What is n? 7 minus 2 is 5. A5B2 and so on. So what are the numbers 7, 21, 35? This number is actually taken from the Pascal Triangle that we just did. Okay, how do you select the Pascal Triangle's numbers? We look at the n number. If the n is 7, you use those numbers in the level of the pyramid. Okay, so question: what is the probability in a family with 4 children? 2 will be male, 2 will be female. So first of all, you must assign A and B, probabilities of each outcome. A male 1 over 2, B female 1 over 2. And then what is the n? N is number of children, 4. So write it out. A plus B to the power 4 becomes A4, A3B, A2B2, AB3. And then you insert 1, 4, 6, 4, 1 based on the Pascal Triangle. So it's A4 plus 4A3B plus 6A2B2 plus 4AB3 and B4. Each term is a possible outcome. In that theorem, A4, A3, A2, A1, in this event, A is getting a boy for children, B is getting a girl. So A4 means that you have 4 boys. A3B, 3 boys, 1 girl. A2B2 is 2 boys, 2 girls. AB3 is 1 boy and 3 girls. B4 is 4 girls. So to actually get a possible outcome, means that whatever the question is asking, you circle the one that is pertaining to that question. For children, you can have all male, or maybe 3 male, 1 female, 2 male, 2 female, 1 male, 3 female, or 4 female. Back to our first question. Our question about how would the possibility be to get 2 male, 2 female. So which one do we select? We take the 6A2B2. Okay, so A2 is for 2 boys, B2 is for the 2 girls. So you calculate, you get 3 out of 8 to get 2 children which are male and 2 children which are female. So imagine you have boy, boy, girl, girl, boy, girl, maybe girl, boy. Okay, that's the idea. Okay, so this is an exercise. First is finding probability of 6 children to get 2 boys, 4 girls. Next will be probability of 4 children to get all girls. Do it. The answer: find probability in family of 6 children to get 2 boys, 4 girls. To get either boy or girl is 1 over 2. Pascal Triangle for n6 is 1, 6, 15, 20, 15, 6, 1. Probability of all children: 6b, 5b, 1g, 4b, 4b, 2g, 3b, 3g. Okay, you know the idea until the end. So we put it into the equation: a6, 6a5b, 15a3b, 3. Right. So this question wants you to have 2 boys, 4 girls. So which one do you select? We select that one that is 15a4b2. We want to have 2 boys, 4 girls. So when we calculate, we put the 1 over 2 into the A and B, you get 15 out of 64. Probability in the family of children to get all girls. So to get either boy or girl is 1 over 2, n is 4. Put into Pascal Triangle, 1, 4, 6, 4, 1. So in the probability, you want to find all girls, so it will be B4. What do you get? 1 over 2 over 4 is 1 over 8. If you prefer not to use Pascal Triangle, you can use formula to determine the numerical coefficient of any set of exponents. N as T. N is the number of events, S is the number of times outcome A occurs, T is the number of outcome B occurs. So N is S plus T. So total number of event, it is the event A and event B happening one after another. Here is the mathematical definition of probability. P is A over N. A is the outcome of interest, how many boys, how many girls. N is the number of all possible outcomes. Okay, like to get a head on a coin toss, 1 over 2. Rolling 1 on a die, 1 over 6. Drawing ace of spades in the cards, 1 over 54. So if P is 0, event is impossible. So you want to roll 7? No, you cannot. So 0. If P is 1, event is certain. So to get a number less than 10, what do you get? 1, because it will happen. Okay. So the real binomial formula hybrid heterozygous, you have n factorial psqt st. And nst, you remember, newspaper times, newspaper, newspaper times, nst. And they have psqt. ps, you know, like PlayStation, and qt, like when you see baby, you call it, you think it's cute, you call it qt. So newspaper times, PlayStation, qt, right? nst psqt. Okay, so what is the exclamation points? It doesn't mean that you have to scream the letter n. No, not like that. The exclamation point is for factorial. So in factorial, it means that you time that number with a number lower than it until you get to 1. Let's say that the number that you select is 3. If it is 3 exclamation points or 3 factorial, it is 3 times 2 times 1. If it is 5, 5 times 4 times 3 times 2 times 1. So this is what's called factorial. Okay, so in the factorial, O is 1. Using formula, let's determine the probability of family of 7 children, 5 be males, 2 be females. N is event. We want 7 children, so N is 7. S is outcome 1, 5. So we want 5 males. Then T is outcome 2, 2 females. So 2. So 7, 5, 2. Remember the theorem NST, PSQT. Okay, so we put the numbers there, 7, 5, 2. Okay, and then PSQT, what do you get? PSQT, P and Q are actually the probability to get a female or male baby. So you do factorial, 7, 6, 5, 4, 3, 2, 1, 5, 4, 3, 2, 1, right? And then we get 7 multiplied by 6, 2 multiplied by 1, okay, and then you get 42 over 2. Then what do you get? 21 over 1 to 8. So in a family of 7 children, on average 21 over 1 to 8 averages to have 5 males and 2 females. Alright, so exercise Binomial Theorem with factorial. Find probability for 8 children to get 3 boys and 2 girls. So you have NST PSQT. N what? 8. S 3. T is 5. 1 over 2 over 3 get what? 1. And then 1 over 2 to 5 you get 64. So we get 7 over 8. Now we move to Chi Square. Chi Square basically evaluates the influence of chance of genetic data. So Mendel gives you the assumption that for monohybrid is 3 to 1. Dihybrid is 9, 3, 3, 1. Okay? Each element is dominant or recessive. Segregation is unimpeded. Independent assortment occurs. Polarization are random. Other fundamental assumptions are influenced by chance events, therefore are subject to random fluctuation. So the concept of chance deviation is mostly illustrated using tossing of single coin numerous times and recording number of heads and tails observed. In each toss, the probability of 1 over 2 that head will occur and probability of 1 over 2 for tail to occur. Therefore, the average ratio of many tosses will be 1 over 2, 1 over 2, so 1, 1. But if a coin is tossed 1,000 times, usually about 500 heads and 500 tails will be observed. Any reasonable fluctuation from this hypothetical ratio, like 514 tails, 486 head, are attributed to chance. As the total number of tosses is reduced, the impact of chance deviation increases. So if you toss a coin only 4 times, there might be a chance of all 4 tails. However, in 1,000 tosses, 1,000 heads or 1,000 tails would be the most unexpected. That it is near impossible to get all heads or all tails. So there are two major points to keep in mind when predicting or analyzing data outcomes. First of all is that the outcomes of independent assortments of analyzation subject to random fluctuation because of chance. As sample size increases, the average deviation for the expected results decreases. The larger the sample, the smaller that it will deviate through chance. Chi-square cognitions and the null hypothesis. In genetics, being able to evaluate observed deviation is a crucial skill. When we assume that data will fit given ratio, we call it a null hypothesis. We assume that because the hypothesis assumes that there is no real difference between the measured values or the predicted values. Any apparent difference may be put into chance. The validity of the hypothesis for a given set of data is measured using statistical analysis. Depending on the result of this analysis, the hypothesis may be either rejected or fail to be rejected. If this is rejected, in that the observed deviation of the expected result is just not to be attributed by chance alone. It is too big for it to happen just by chance. In this case, the null hypothesis and the underlying assumptions leading to it must be re-examined. One simple statistical test assuming the goodness of fit of the null hypothesis is the chi-square analysis. This test takes into account of observed deviation in each component of the ratio of the expect, as well as sample size, and reduces them to a single numerical value called the chi-square. Value for a chi-square is the frequency of observed deviation can be expected to occur strictly as a result of chance. The formula used in chi-square analysis is chi-square equals sigma O minus E squared over E. O is observed, E expected value for the category. Sigma is sum of the calculated values of each category in the ratio. O minus E is deviation D in each case in, and each equation reduces to chi-square sigma D squared over E. Okay, so here is the steps to calculate the chi-square for actual results of hypothetical monohybrid cross. So expected, what we learned from Mendel is 3 out of 4, 2 out of 4, so 3 to 1. Okay. We observe 740 and 260. Okay. So what do you expect from Mendel is 3 out of 4 are dominant and the remaining is recessive. So it should be 750, 250. So first of all, find the difference between the expected and the observed. 740 minus 750, 260 minus 250. So what you do is that you square the number. We get 100 and 100. So this number 100, we divide it over the expected, which is 750. Why do we do this? To measure how far is it, how big is it compared to the expectation. In the terms of difference, how big is the difference? So 100 over 750 you get 0.13. 100 over 250 you get 0.40. So the chi-square will be 0.53. So using a probability table, chi-square for this is 0.48. In the hybrid, we do the same thing. Okay. First of all, we establish the expected ratio of the hybrid 9331. Now 16, 0, 16, 0, 16, and 1 16. And then we put the number of observations. It is observed, the one which is That is, dominant is 587, then you have 197, then 168, and then the recessive is 56. Expected, okay, you look at total 108, and then you times the cross expected ratio 187, 189, 189, and C3. Next, you find the difference. For the dominant is 20, the other is 8, and the other one is minus 21, and the recessive is 107. And then you square the differences 464, 441, and 49. And then when you find the differences, you have to divide with the actual expected number. 400 over 567, 54 over 189, 441 over 189, and 49 over series 3. So what we get is the chi-square number 4.16. What do you get? In terms of probability is 4.26. So regardless whether the deviation or the differences are positive or negative, when you square them, they'll always become positive. So how do we interpret the chi-square value? First of all, you must determine the degrees of freedom. So degree of freedom will be number of different categories in which data are divided, meaning that how many possible outcomes you have. So in this 3:1 ratio, you only have two categories, either dominant or recessive, right? So two categories, n is 2. The degree of freedom will be 1. So that's n minus 1. For 9:3 ratio, we have 4 outcomes, okay? N or 3 or 3 or 1. So we have n is 4. Degree of freedom is 3. Okay. So the greater number of categories, the more deviation are expected as a result of chance. Chi-square value is interpreted in terms of corresponding probability value. Since the coefficient is complex, you usually take the p-value from the standard table or graph. So in figure 311, it shows you a wide range of chi-square values and corresponding p-values for varying degrees of freedom in both graph and table. So using this, you explain how to determine p-value. If you look at the caption there, small writing, it determines how to find the p-value and how to find table. Okay, so let's say in the first calculation that we have, it is p is 4.48. Right. And so what is degree of freedom? We only have two categories, right? So degree of freedom is 1. So you take that number, so degree of freedom is 1, and then what is your chi-square? Your chi-square is 1. Okay, 0.53. So you use your ruler, you try to put that and measure it all the way to the y-axis. What number you get is 0.48. Probability is 0.48. It means that it is significant. It means that the hypothesis is not rejected. It still follows Mendel. The deviation is just by chance. Okay, what about the second one? Okay, in the second one, now we use the table. So the one that we have, the chi-square, is what? What we get is 0.46. But what is our degree of freedom? Degree of freedom is much more bigger. Okay? So with that big degree of freedom, because now we have 4 values, so the degree of freedom is 3. So the number that we have found, found from that calculation, compared to this number in the table, it is actually more than 0.5, meaning that we fail to reject the hypothesis. We reject the hypothesis. So it means that the deviation is not by chance. If you want to look for the hybrid cross in the table B with the 4 values, the chi-square value is 4.16 and df is 3. Pascal value is 4.26. Meaning that the values of non-hybrid and hybrid cross are between 0.20 and 0.50. Meaning that it is still significant. So p-value is a percentage. Okay, so the number of hybrid cross interval between 2 to 3, p is 0.26. We call it the 26%. Meaning that if we repeat the same experiment many times, 36% will have greater chance deviation as green. greater than seen in the initial trial, meaning that it is quite low. Conversely, 74% would show less deviation due to chance, meaning that they will follow Mendel's theorem 3 to 1 in terms of ratio. For p-value, reveals that HO or null hypothesis concerning the 9:1 ratio is never proved or disproved absolutely. So because of that, we set a relative standard that we use to reject or fail to reject the hypothesis. The standard will be a p-value of 0.05. If you have 0.05 value, mean that the deviation by chance is minus or lower than 5% at the time, meaning that you really have a strong data, and the data is strong enough that the error probability is so low, meaning that 5% error, 90% you have correct, so you have 90%, 95% of correct data. So for p-values more than 0.5, means that deviation can be achieved by chance alone 5% or more of the time. It means that if you have more than 0.05 p-value, means that you can reject the null hypothesis. So p-value is 0.26. The null hypothesis, which is independent of causes the result, failed to be rejected. Therefore, the observed deviation can be reasonably attributed by chance. So, what is the alternative interpretation of data? So, we can say that segregation operates faithfully for both gene pairs, and we assume that fertilization is random, probability of gametes are equal regarding to genotype. But we assume that in fertilization, all without stages and offspring are equally viable, meaning that no matter what kind of allele that they have, all of them are able to be born, regardless of their phenotype. But there can be an exception. If any of these assumptions are incorrect, then the original hypothesis is not necessarily invalid. For example, you have the hypothesis that hybrid cross between fruit flies will result in 316 mutant embryos splice. However, perhaps fewer of the mutant embryos are able to survive their development or young adults compared to flies with genotype give rise to wings. Meaning that in this freak accident, somehow the wingless one survive and the winged one, they die first. That when you count it, it's like, oh, it's not 3 to 16, it's more than that. Okay, so you must think before you reject. Rejection of null hypothesis is not itself the cause for us to reject the validity of postulates or segregation and independent assessment, because there might be other factors that we are unaware of, may also be affecting the outcome. So, example, in Mendelism cross, you cross the yellow round and green wrinkle. Okay, so at point you get the yellow round. You self-fertilize it, you have 315 yellow round, 108 green round, yellow wrinkle is 101, green wrinkle is 32. You get 9, 3, 3, 1. You follow the classic Mendel ratio. So if you calculate the observed versus the expected, there will be a little bit of a small variation in each one. In a hybrid cross with champion done by Hoover de Vries, it doesn't actually follow the Mendel's distribution. There are red flowers, hairy foliage, crossed with white flowers and smooth foliage. So foliage means leaves. So therefore you get red flowers with hairy foliage, meaning that you might think that okay, hairy foliage and red flowers are the dominant. But in F2, instead of having the 9331, you have 4121. Hairy foliage and red flowers is 70. White flower and hairy foliage is 33. Red flowers smooth foliage is 2. Meaning you have 46. White flowers and smooth foliage is 1. So you have 4121. It's really different compared to Mendel's postulates. So which one is real? We do a chi-square on both and find out. Okay, when we do a chi-square for the P plants, it is 0.51 chi-square. But we do it with the de Vries hybrid cross, we get 32.94. Okay. So when we look at the chi-square table, okay, how much decay freedom that we have? we have non-trivial in that 4 values. In terms of a given video, we have 3. So to actually get 0.05, the critical value must be 7.815. Compare it with our chi-square. For Mendelism cross, chi-square is 0.51, but critical value is 7.815. If yes, chi-square is 22.91, compared to the critical value is 7.815. What does it mean? It means that hypothesis of the null hypothesis for Mendelism cross is correct. That even though there is a little bit of error, it still follows the Mendel distribution. What about the AVS? The AVS is so high compared to the critical value, which is 7.8, meaning that you can reject hypothesis. It doesn't follow the Mendel distribution. Here is an exercise. So solve this using the formula method. Now use the chi-square. Can you do it? Here is the chi-square value. The end.